Sorry, we just had a few display issues, so that just delayed a few things. So first of all, are there any major questions or concerns about the midterm? I mean, besides the fact, yeah, okay, I cannot tell you that. Or the answers for that matter. Well, I mean, well, Geoff and I have been telling you the answers all the time, so yeah. Okay, so you have the answers, you just don't know the questions yet, right? We'll try to have questions that are in line with what you've seen before, so you shouldn't be too shocked. Yeah, taking with you one sheet of paper. So this is not an exercise in having the smallest font size. I think those who, can write Chinese characters are probably at an advantage here, because the information density can be higher. But the point is more, this might actually help you to think about what's really important, right? Go crazy and do the equivalent of a microfiche, and you need to use a magnifier to read it. Spend the time to understand the math instead if you can. Any other questions? Yeah?
This one's kind of silly, but do you mind if it's typed?
You can do whatever. So
anything that doesn't involve an electron microscope.
So you can type it, you can photocopy it, you can scale it, you can do whatever you want. But the point is there are diminishing returns. And yes, I'm aware that people with eagle eyes and a high resolution printer might be at an advantage, but yeah. Okay. Anything else? Okay.
Review session tonight?
Yes. So
6 p.m. Review session tonight at 6 p.m. here in this room. Ask me questions, I'll try to answer them.
okay. Good. So we're going to do one more sweep through kernels today, and I'll pretty much conclude kernels as far as this class is concerned. They'll come back a little bit in the context of Gaussian processes and Bayesian methods later on, but today is the end of kernels for better or worse. Yeah, at least in terms of the class, right? Let's just briefly recap what we did on Monday. We had a maximum distance hyperplane which separated the data from the origin, and the idea was to use this in order to identify novel observations. And if you recall, we got this as an optimization problem out of it. So the primal problem was basically minimize 1/2 w squared plus c times sum of the i's under this constraint. And then we wrote the Lagrange function, and everything was cool. And then we looked at the dual problem, and basically all we had to do is just take the derivatives with regard to w and psi, and everything was good. So quick question before I move on. Why didn't we need b in that optimization problem? Basically, why didn't we need constant offset here? It would go wrong if I added a constant offset. Exactly. So you could always take, as small a w as you'd wanted and make b large, and since I'm not utilizing it, well, I can, move that hyperplane out as far as I want, so I get nonsensical solutions. Exactly. So that's why we don't need b. And the interesting thing is that by getting rid of b, we also got rid of one constraint in the dual. So if we move through, we see that, well, this looks pretty much like our standard SVM problem. These are the box constraints that we had before also from SVM classification. But then there's this one constraint missing, right? In SVMs, we had this constraint sum over I. Okay. Sum over I, alpha I, yi equals 0, right? This constraint came from the fact that the derivative with regard to b of the Lagrange function had to vanish. That's where this guy came from. Now, since we don't have b, we don't get that constraint. Pardon?
We also don't have yi's here.
Correct. We don't have yi's here.
Explain again why.
Well, okay, so why don't we have labels for novelty detection? Well, if I knew what was novel, this would be a classification problem, right? But since I don't know what's novel, basically since I don't know the question yet, well, I cannot really learn the answer.
Okay, I thought classification.
So this is really just for, novelty detection. If I didn't have a constant offset for SVM classification, I also wouldn't get this, right? So if I wanted to solve an optimization problem just of the form, w.x greater or equal than yi, greater or equal than 1 for y, y equals minus 1. Case of what I alluded to before, namely that free variables give equality constraints, and the other thing is, of course, equality constraints give rise to free variables. So we know that from the Lagrange function that you basically, if you have an equality constraint, you just add a Lagrange, you multiply it with the Lagrange multiplier and you add it in. There's a question.
So does this mean that if you added a column once to your X matrix, you would break this?
So if you add a, brilliant question. Brilliant. So let me write this out. This is a wonderful question. So let's say rather than taking xi's, I transform them into xi and 1, right? And if here w was in Rd, let's say here it would be in Rd plus 1. And exactly as you would expect, you would get that, well, actually, let me put the 1 here and make this the 0th coordinate just to make it a little bit nicer. So I have 1 dot xi dot w naught and w. This is basically, my 0th coordinate, which is as what we had before, xi dot w. Yeah, plus w0. Okay. So this is our b, right? So what's different between this and what we have here? Does somebody have an idea what's different? And the difference is subtle. This is, by the way, a great question. Any ideas of what's different? So when we have the b, it's unconstrained, right? Here, when we have the w0, it's also unconstrained, so that's the same. The functional form is the same, so there's no change here either. Yet something is different. Okay. Exactly. That's exactly the difference. That we now have a norm of w naught and w squared, which is, of course, nothing else than w naught squared plus norm of w squared. Right? Now, in other words, this actually makes us pay a penalty for having a particular large value of a constant offset, whereas previously we didn't pay that. This is arguably a more sane solution because it basically, you don't really want to have absolutely huge offsets in general. However, it turns out that quite often if your data is not centered, having an unpenalized b will essentially take care of all the centering and be a better solution. So in other words, if you've centered your data before, this is probably better and easier to implement. If you didn't center your data, then use the one with a b. So that's more or less the idea behind it. Okay, because recall when we derived the original SVM problem, the relative position, so only the relative position of the xi's with regard to each other mattered. The absolute position was completely irrelevant. Okay? Whereas here, Of course, if I shift all the guys, then, well, what will change is definitely this B, and that's penalized here. Okay, great question. Any more questions of that kind? I love them. Okay, yes?
So you said about the two cases where you segregated in, that's for the SVN, not for the...
Well, so for novelty detection, if you center, it actually changes the problem, right? Because, well, let's go back. Okay, let's say I want to center this, right? Then this is mission impossible, right? That is not quite mission impossible in high-dimensional spaces, because you would really not want to do novelty detection with linear features. It doesn't work terribly well. It doesn't work terribly well exactly for this reason, or there you can see why centering is, well, okay, so centering in that space wouldn't really help you that much either. But, so you could actually write this out directly as a minimum enclosing ball problem. And then again, the offset doesn't matter. Okay, good. So now here comes actually a rather pesky problem, right? So if we look at the, this optimization problem, and, we have, those box constraints, and, that's kind of nice. But then, I run my novelty detector, and whoops, it comes back with, by the way, half of your data is considered novel. That's often not really acceptable. For instance, if you're, using this in a computer security setting, and your, basically intrusion detector, whatever, flags half of your data as suspect. Well, that's no good, because basically you're essentially performing a denial of service attack on the poor systems administrator who now has to go through each of those cases. What you would much rather want to have is a setting where I say, well, the poor system admin can maybe handle 10 cases a day, and I want my system to identify the 10 worst cases every day. Or, for instance, if I have, the car that is self-calibrating, then maybe I'm willing to tolerate if it goes off once every year, maybe even once every week, but I don't want it to go off a lot and at some point just because, well, the engineer who set this up set the C parameter in the wrong way, right? So that's a lot harder to quantify than saying, well, I want it to go off maybe once every year. And so there's actually a nice trick how you can get this. So if you think about it, what really happens here is, well, I can gauge how novel or how common observations are considered by shifting that hyperplane, right? If I move it towards the origin, more observations are considered typical. If I push it further out to the right, more observations are considered novel. So in other words, I can actually make this offset itself part of the optimization problem. So this is something that people don't really do enough, even though it makes your entire problem very, very easy to control and to use. And by the way, you can use the same thing for classification, where I might just say, well, I expect to have maybe 5% training error. Doing a brute force grid search over all the parameters until you get 5%, right? So the problem is really, we want to actually specify beforehand at what approximate error level you train. Remember that this is actually a hard problem if I want to do it exactly, because, well, Minsky and Papert, minimum error classification with a linear separator is hard. If I pre-specify the error level, it doesn't get much easier either. So, however, what you can do is you can basically say, well, we don't really care about the boundary cases. So if I have observations here, here's the origin, then if I don't really care very much about, how I count those points exactly on the boundary, then I can actually turn this into a polynomial problem, as a polynomial time solution problem. And the way I do this is by saying that, well, I want to find a hyperplane, you know, w.x, but rather than setting it to 1, I set it to rho. And I make rho itself a variable of the optimization problem to be adjusted in such a way that it gets it just right. So if I make a rho larger, well, it'll consider more observations as novel. If I make rho smaller, it'll consider more of them as typical. Okay. So does that sort of make sense, right? So here is what we can do by adjusting rho. That's what we have is w.x equals rho. And here's how you get it. So this is the same optimization problem as what we had before. W.x plus psi I greater or equal than rho. So where we had a 1 before, now we have a rho. So this is the green line. The psi i's have to be greater or equal than 0. That's just as what we had before as well. Now the objective function is the same throughout with one exception. Of course, we would like to have a large rho, because large rho means hyperplanes far on the right. So if I have a small rho, I have to pay a penalty. And so what I therefore do is I just add minus m times nu times rho. And I'll get to it in a moment how exactly on earth you come up with m times nu times rho. And so we'll analyze this optimization problem in a bit more detail. Okay. So is everybody cool with the primal problem? I'll derive the dual, don't worry. Is everybody okay with the primal problem? M is sample size. So I going from 1 to m. So if I have 1,000 observations, m equals 1,000. Right? Yes, so nu is a ratio. You're basically already of what I was going to do. Nu will be exactly the fraction of points that are to be considered novel. So this will be a number between 0 and 1, and we're actually going to derive this. So given that that question already came up, let's first actually try to understand what happens. So we'll derive this in a moment, but this is the dual optimization problem, which looks exactly like what we had for novelty detection before, but we have one extra constraint here, this part here. Sum over alpha I equals nu times m. And the alpha i's are between 0 and 1. So we know that all the points which are here, they have an alpha I equals 1. We know that those points here, okay, what's their alpha I? Equals 0. Perfect. And for those, it's anything in between, right? So now what I have is that I know that the sum over the alpha I is the same. We'll derive that, don't worry. So what does this mean on the minimum number of alpha i's that have to be non-zero? So let's say m equals 1,000, 0.1. So sum over the alpha, each of the alpha i's is bounded by 1. How many alpha i's at least have to be non-zero? 100. What's the maximum number of alpha i's that can be non-zero? 1,000, exactly. So I don't really know whether, it's 100 or it's more than 100, as it could be all of them. What would it mean if all the alpha i's were non-zero? Where would the data points lie? They would be on the boundary, or they could be on the wrong side. So basically in that really horrible situation where all the alpha i's are non-zero, I would have points exactly here on that line and over here on the left-hand side. In the case where only 100 of them are non-zero, I will have 100 points exactly either on the boundary or to the left. And everything else has to be strictly to the right. Okay? So this already gives us a very nice property. It means that the number of support vectors, or support points in this case, is at least nu times rho, nu times m. And we therefore also know that the points that are on the right is at most 1 minus nu times m. Okay? What I'm going to do is, in a moment, is actually to derive what the fractions are, and basically there'll be 3 sets of points, those on the left, those on the right, and these on the boundary. Those on the boundary bother about time, turns the problem from NP hard, not bothering about those points in detail. Okay. So let's quickly go through the optimization problem. So the Lagrange function is 1/2 w squared. Does everybody want me to go through this, or should I move on? Because I mean, it's exactly the same mechanism as what we've done so far. Who wants me to go through the derivation? Okay, majority. Plus sum over I going from 1 to m psi I minus m times nu times rho. And then we have, in addition to that, minus sum over I alpha I. Here we have w dot xi minus rho plus psi I. And we have minus sum over I eta I psi I. So the first set of constraints comes from the margin constraints. This one just says you cannot benefit from doing better than what you expected to do on those points that are already correctly classified. So this comes from the fact that the psi i's have to be greater or equal than 0. Okay? So now all we have to do is take derivatives. So dw of L equals w, and then we have minus sum over I alpha I xi, and that's about it, equals 0. So therefore we have w equals sum over I alpha I xi. Right? This is the support vector expansion. That's also called the representer theorem. Secondly, we have d rho of L equals, well, here we have minus m times nu plus sum over the alpha i's equals 0. So we have m times nu equals sum over alpha I. That's this rate constraint on the right. And then we also have the psi I of L is, well, 1. That's the guy up here. And then we get minus alpha I minus eta I equals 0. And so we get the well-known constraint that the alpha i's have to be in the interval between 0 and 1. And we can afterwards get rid of the etas. So I've just derived all three constraints. This, that, and then the solution for W. Okay. And now all we have to do is just plug terms in. And this is particularly easy because all the linear terms we can knock out right away anyway. So this goes away, this goes away, this goes away, this goes away, and that goes away. So then we are just left with sum over alpha I xi dot w minus that plus 1/2 w squared, which you can immediately identify as being minus sum over alpha I alpha j xi dot xj, and we're done. Because this thing here and that thing there are the same. Okay. Is everybody cool with that? Any questions so far? Yep. There are actually no yi's here. These are etas.
So that last term you're going with function minus sum over I.
Correct? Correct, yes. Sorry, my handwriting's appalling. That's why I use slides usually. Jobs is way nicer. Okay, any other questions? Okay, so this is what gives us a dual problem. And so then, well, we can just, write out the dual problem. And as a matter of fact, we have a rather nice property. Namely, at most, as we discussed, the fraction of new points are novel. And at most, the fraction of 1 minus new points aren't novel. And, well, the other thing is that, and this is a little bit harder to show, that the fraction of points on the boundary vanishes for large sample sizes. So that is actually due to the fact that this boundary have a particular pathological kernel is a set of measure 0. So unless I have a really weird distribution and a really weird, those things will never give me some trouble. Okay, but let's actually prove the first two parts of the claim. It's a very simple proof. And it basically works as follows. I'm going to sit at the optimal solution and then I say, well, what if I moved that plane a little bit to the right, and what if I moved that plane a little bit to the left? Okay. So I have three sets of points. I have the m plus, which is not novel. I have the m zeros, which are on the boundary. And I have the m minuses, which are novel. Okay, and of course I know that m plus plus m0 plus m minus equals m. Right? So now, if I move that plane a little bit to the right, what happens is that those points here that sit exactly on the boundary will all of a sudden become, properly novel points. So I pay, okay, so what am I paying is m minus plus m0 times nu times, delta rho. Okay, so I have m minus plus m0 times, well, nu times delta. So this is the penalty that I'm paying. Sorry, there's no nu here, times delta. But I will also gain, namely, m times nu times delta. Because now my margin is larger, because my hyperplane is larger. On the other hand, if I move it to the, so this is to the right, And if we move it to the left, then what happens is I have the points m minus, because for the m zeros I'm not paying, times delta, and here I have plus, so I have, sorry, no.
You are shifting or moving.
Pardon?
What's delta?
Delta is the amount that I'm shifting. And here I have m times nu times delta. And so what I need to have is that things get larger on both ends, otherwise I wouldn't have optimality. Now if you work out those ratios, you get exactly this inequality here. Namely, the fraction of novel points is upper bounded by nu, which is a lower bound on the fraction of typical points. This is something that we already saw on the previous slide, sorry, 2 slides ago, just from this inequality. We worked it out directly here. So you can work it out just by looking at the algebra, and it's perfectly reasonable. You work it out using geometry. That's also perfectly reasonable. So it's your choice, whatever you like better. I find this a little bit easier to understand when you want to develop intuition, and later on you switch to the optimization problem directly. The same argument, by the way, also works for classification. Because for classification, we can also play with the width of the margin. So I can make the margin narrow or wider. And if I make the margin very narrow, then it's easier to solve this problem. But then, I don't have quite that much of a penalty. So rather than setting it to 1 or -1, I can set it to rho. And this gives me an optimization problem classifications. Get exactly the same type of a condition such as here. So, fun?
Are you assuming that there's not a lot of points near the margin so that when you move it to the right, you don't capture a whole lot that we're not?
That's a very good question. So the question was, am I assuming that by doing this, reasoning of shifting the boundary, there aren't, I'm not going to run into anything else? Well, yes and no. I'm assuming that there is some non-zero shift that I can perform, regardless of whatever small it is, that will not run into new points, right? And since I have a finite number of points, it always exists. And so therefore, since optimality has to hold at this point, I can just make an infinitesimal shift. I can always shift less than how much closer you can move your points. So this is why that doesn't really matter for the purpose of the proof. In practice, yes, okay, sure, this may influence your solution quality a little bit. Okay, so let me show you a little bit what happens. So here, well, it's just some data. I set nu equals, 0.5, and we picked, some width of the kernel, and then you get, that the number of support vectors is around 0.5. So you can see it's not exactly true because there are points on the boundary. That's the size of the margin. Now, if I have some additional points on the upper left, the fractions don't actually change very much, but the points that are being chosen as novel are now different, namely typically the ones on the upper left. Now, if I change the kernel width, so this is a way of quantifying what I mean by smooth function. It'll actually consider this as 2 cases of, typical points with, novelty on the boundaries. Of course, if you have garbage, then, there's not much you can do. Basically, if you have a very narrow kernel, not so meaningful. So what this tells you is that novelty detection is not quite that well defined in terms of, whether there's a clear objective function. The only thing you can say is, well, these regions have low density relative to what I consider a well-behaved function. So you might say, well, what's the entire point of this? Well, this, I think, should show you that, well, the digits are a lot uglier. So what you see from left to right are the scores. Basically, very negative means very novel. And the number to the right of that is what the digit actually should have been. So that blob on the upper left was supposedly a 9. And you can see that there's basically wrong segmentation happening. So whether this is 0, mind you, this was a US data set, so it's clear that this is a 5. Well, you could really argue that this is a 0. Well, this looks very much like a 6 to me, and so on. So this actually shows that there's a lot uglier data in that data set, and by being clever about optimizing, by actually optimizing for low density regions as opposed to just using a density estimate and then thresholding, you get something very meaningful. The really fun thing is that if I set nu equals 1, remember we had this condition m times nu equals alpha, sum over the alpha i's. If I set nu equals 1, I get that m equals sum over the alpha i's, and the only way I can satisfy this is by setting all the alpha i's equals 1. Right? And this is exactly Parsons Windows. And that's what you would expect, because Parsons Windows effectively, considers all the observations as, quote, novel, and then sorts accordingly. So it's kind of, reassuring that you get an existing technique out of it as a special case. And yes, you can use the new trick for classification, and you get similar things, and maybe we can do that at some point in recitation or as an assignment, or you can just read it up. Yep. So this is what the new trick is all about. Any questions so far? Yep.
We might not know mu. However, the OCR problem, we might know the number of classes. There are 10 digits, so we have 10 classes that are there. That's like, how do we incorporate that information, and how do we estimate?
Okay. So knowing the number of classes, in this case, I wouldn't directly know a really nice way to capture this. The way to capture this would be basically probably to go back to the original problem of, thresholding densities. Then maybe imposing a mixture style model and optimizing over this problem. If you do this well, you can probably write a paper about this. I don't know whether it would fly at NIPS, but it would probably fly at a slightly less amazing conference. So this is low-hanging fruit if it hasn't already been done. Now, what you do know, though, is, for instance, for classification, let's say your job is to solve an OCR problem, right? Optical character recognition. And you know that an acceptable error rate might be, 0.1%. Then you can set nu equals 10 to the minus 3, and it'll give you a good starting point. So in other words, quite often you might have some pre-estimated guess of, what a reasonable performance should be, and that's just what you start new with. So this is a lot more meaningful as a quantity rather than just picking C to be 42, right? So in the early days of support vector machines, I think every month I got an email of which value of C do you pick, 2 or 3? This is not a meaningful question. Okay. So one thing that I haven't really told you about is how you solve large optimization problems. So this is just a list of, simple tricks that you can use for SVMs or other problems of that form. So I'm going to look in general at, a constrained quadratic program. So I minimize, 1/2 alpha transpose Q alpha plus L transpose alpha, subject to some constraints. And for small problems, you just use off-the-shelf solve. But the thing that you could do is you could also, solve a sequence of subproblems. And each of those subproblems is farmed out to an off-the-shelf solver. Or you optimize in primal space directly. And all of those things can actually give you something meaningful. So I don't know how well it renders here. Well, sort of, kind of, okay. This might be a constrained optimization problem. So basically each of those planes is a constraint. This is my objective function. I want to minimize this. And yeah, I'm sorry, the brightness level of the projector kind of kills it. If you download the slides, it'll be a bit more useful. But essentially what you want to do is you want to find the solution within this region. And let's assume this is really big and complicated, so you can't really take a solver for that. So what you could do is you could just take a subproblem, right? And of course, if I take a subset of variables, if the original problem was a quadratic program, the subset is also again a quadratic program, right? This is just like coordinate descent, right? So you've probably implemented coordinate descent at some point where you have a big complicated function of many variables, and you take one variable at a time and update. Those things can be awfully slow to convert if I don't have a good solver, but they can be actually quite efficient if I just get the order just right. In any case, well, what we can do is we can reduce this into a subproblem. Let me just briefly show you what happens for this decomposition. But okay, so is this transition from up here to there clear to everybody? Who wants me to explain it? Okay, that's a small number of people. Yes, so let me explain the notation at least. So Q is a matrix QAA. That's with A I mean active and F I mean fixed. I have QAF. I have QFF. Okay, what needs to go down here? It's a symmetric matrix, yes. So what do I need to write down here? QAF, is that correct? Transpose, exactly. And then L is just, LA and LF. Mind you, these don't have to be contiguous sets of vectors, but it's just really awkward if you don't write it out this way on paper. Okay, so now I do this. I plug this into the optimization problem up there, multiply out all the terms, throw away everything that doesn't involve alpha A, and everything that's fixed, well, okay, just add it to the fixed terms, right? That's what I get here. So I do the same thing for the constraints. So now I have a smaller problem. And this is probably small enough that my solver can solve it. And then in some cases, I take only one or two variables at a time. There's a very famous example of that. It's called the SMO algorithm. This is by John Platt. Sequential minimal optimization, something like that. So he's the only machine learner I know who also has an Oscar, as in Hollywood Oscar. Yeah, for simulations of digital hair. So it's the Oscar for nerds that he got. And he's a really cool guy. Anyway, so this is what happens. So this is if I pick out, one-dimensional problem, and I move along this line and I solve it. Okay. So I end up maybe somewhere up there in the middle. Then I pick a new line, I solve that, and boom, I'm already here in my solution and I'm done. So then the obvious question is, which subproblem should I pick? Well, obviously, those points that are, perfectly classified, I don't have to worry. Those points that are hopelessly wrong, I probably won't have to worry either unless I get things right otherwise. So the ones that I really care about are those in the boundary region. And so this is exactly what you use. You basically look at the Kuntaka conditions. We know that constraint times multiply has to be 0. And then look at how much this is violated. And that gives me a good recipe how to prioritize. So in other words, if I have a point here, which is perfectly classified but has a non-zero Lagrange multiplier weight, I throw it in, ditto there. If I have a point that's wrongly classified and has a 0 weight, I throw it in. And well, I just correspondingly multiply again. And this, well, will give you good progress. And there are theorems which tell you, what rate you get depending on which specific strategy. And that's actually been used with great success. And if you have a moderately sized problem, this is a good idea. For very large scale, this doesn't work, but for moderate sized problems, this is actually pretty good. So SVM Lite, for instance, does stuff like this, so by Thorsten Joachims. And this will work well for, a couple of 100,000 of observations, 1 million probably if you have a lot of time on a big machine, but that's about it. So let me show you a little bit what those various algorithms do. So chunking, this is if you pull out an old SVM paper, that's how they called it, because essentially people built those problems and they didn't know convex optimization. So machine learners reinvented a lot of stuff that was very well known for optimizations people, and well, the latter initially just laughed at it and it's like, hey, well, can they really be doing something as stupid as that? Then they started taking it seriously, published a few papers, and the field moved along very much so, to the extent that by now machine learners are writing optimization papers. So it's kind of fun how it evolved. And then Edgar Ozuna came along around 97 or so and said, well, hey, we can actually do this even with variables that are non-zero. This is basically take small enough subsets and add points in. And this is the most elegant solution, SMO, sequential minimal optimization, where I take pairs of variables at a time and I optimize them. Quick question. Why do I have to pick pairs of variables rather than a single variable? So they need to, well, you could form a line with a single one, right? So the reason why I need to pick pairs is because I have this pesky constraint. Because I have sum over alpha I y equals 0. So if I change one variable and don't change any of the others, I can't really change that. I need a variable to move in the opposite direction. And this is exactly where this very nice question from before can be very useful. Namely, if I don't quite solve that problem, but I actually penalize B, I lose my translation invariance, but my code gets about twice as fast. So you win a lot. Okay. Another thing that's, I think, really useful to keep in mind is that it pays a lot to be smart about the hardware. So this is the only hardware-oriented slide in this class today. But let's just look at I/O speeds and what your machines can do. And these are ballpark figures, and you can probably get stuff that's off in either direction by a factor of 2 or 4. But okay, so your hard disk, 3 terabytes is kind of what you buy for between $100 and $200, depending on whether you want to have an enterprise drive. That's about what you get in burst read. So basically, if you sequentially read, that's about what happens. The number of IOPS, so the access, why I cannot. There's a seek time. Okay, so why is there a seek time? Why hasn't it changed, right? That seek time has been around 2 to 5 milliseconds, maybe 10 milliseconds. And it's been like that for at least as long as I remember buying hard drives. Why?
Because the reader has to move physically.
Exactly, because it's a physical constraint. So that head that moves along the disk has to actually move. Now, if you move that way too fast, it snaps right off. So it basically is a constraint that, you can't then steal too much or you can't accelerate things too much, otherwise you trash the hard drive. This is why it's simple physics that keeps this number low. Okay. Now, SSDs, actually those numbers are a little bit dated. You can now get actually one order of magnitude more. So last year when I made this table, it was 50,000. That was kind of a good number. But now you can buy hard drives at a reasonable price, SSDs that have 500,000 IOPS, which is quite amazing. By the way, they don't have that doesn't actually translate into amazing latency. Why is there a difference between the number of random reads that I can get through versus random reads that if I don't queue things up? Well, because basically they still need to read from block memory. And what essentially the algorithm in the controller does, if it's a good controller, it reorders things in such a way that you sequentially go through things in a reasonable way. This is why you want to queue up your requests. Okay? Sounds like, okay, all of a sudden, whoa, we are going from convex optimization to really into the nitty-gritty details of hardware. But I'll show you in a moment why this is actually worth it. Main memory, well, 16 gigabytes is still a decent machine, so you can buy laptops with that size by now quite easily. The memory bandwidth is a lot higher. That number, okay, maybe a factor of 5. This number here, it's more like a factor of 10, depending on a desktop, you can get up to 100 gigabytes a second. Number of random reads is also a lot higher. So you're paying about maybe between, 10 to 100 nanoseconds for requests. For cache, it's even higher. So now if the data flows from the disk to memory to then, doing something with the data, if you're working on big data, well, you can hear people talk about algorithms where, essentially they are I/O bound, right? They tell you that, well, you can't do really anything smarter about this problem because you simply cannot get the disk off the data fast enough. This is a sign of people who haven't really thought deeply about the algorithm, right? Because if you have extra CPU cycles to spare, you want to use them. Okay. So what you basically do is once you've read the data from disk, you use it several times before you throw it away again. And that's the trick. So if you do this, you can get that kind of result. This is a paper that we had last year. And this was basically the fastest competitor. And we were basically, by the time this algorithm got started, finished creating its data representation on disk. So the way it works is it's so ridiculously simple. But it's those little tricks that really make a big difference. You basically have a ring buffer. And you write from the disk into that ring buffer. And you then have your CPU, which reads from that ring buffer. Now, the CPU can go around maybe 10 to 100 times in the time it takes the disk to write. And as long as you're reasonably careful about not reading stuff that's just being written at that point, and that's just basic computer science, you can get these fast rates of convergence. So we are much faster by simply processing the data several times, whereas everybody else just uses it once.
The vertical axis is time, right? Horizontal axis is what?
So horizontal axis is time, vertical axis is accuracy. Yeah. This is about where you stop caring about the accuracy, actually. So, and this is, there's almost no math involved in this. It's really just exploiting the fact that, you have a computer with certain resources. And if you ignore the fact that you have a computer where certain things are fast and certain things are slow, well, your algorithm will never be good. Okay. Worry about those things if you can get a factor of 10 or more speed up. Don't worry about it for 20% speed ups. Unless you're a high frequency trader, or you have a deployment of maybe 10,000 machines where 10 to 20% speed ups actually mean a lot of less machines used. So basically in reality, worry about orders of magnitude. Yep?
What do you mean by using data repeatedly?
So if you look at what happened here is you basically have a choice which variable you reuse. And so if you have to read your problem in from disk, then you have a certain window of, where you can actually optimize over it easily. You do that, and then you just move along. And this way you make faster, you get faster convergence. And yeah, you can prove theorems for it. So yes, there was math involved in that paper, but the basic idea really was just this simple idea. Okay.
Actually, I don't understand the previous picture you were showing there were blocks.
Okay, so this one here. So those blocks, okay, thanks for asking. So those blocks are basically the variables that you optimize over at any step in the optimization problem. So in SMO, you pick pairs of variables. And for those, you can actually solve the quadratic program analytically. Well, it's very easy because we know how to minimize a quadratic function on paper. In one variable, we know how to do that. That's exactly the problem you get there. The only thing is you have to worry about the boundaries because you might have hit one of them. So basically you need to distinguish 3 cases. You can solve it all in closed form. So each of the substeps is blazingly fast. There you take subsets of variables and you just add them in as you go along. Chunking just picks different other subsets. Any more questions about that? Thanks for asking.
Is there a fraction of the total number of data points that's kind of good? Because if we go down to 2, we're probably taking a whole lot more steps. And we have the entire data, we just
Correct.
a lot.
Correct. So the question was, is 2 really a good number? Well, you could pick a slightly larger set. People do by now, though, is they solve the problem in a slightly different way directly in the primal, where this sounds kind of counter to all that I've been telling you about SVMs. So it turns out that by now there are a couple of techniques which will give you a very high dimensional but easy to compute approximate feature-based representation. And you do that when you have billions of observations. So this is not a problem if you have smaller data sets of maybe a couple of 100,000 or 1,000,000 observations. But as soon as you go to billions of observations, you can't really solve it in the dual easily anymore. So this is where actually all the really fun things start, because it's like you're given a puzzle, you have to solve it, you have resource constraints, and basically the way you solve it is you assume a solution exists and then you work backwards from that. And that's actually a very good technique of solving problems. Okay. Yep.
So in the SMO case, which is the best, you said we select 2 features at a time.
Mm-hmm.
What if it's like how do we optimize on the number of features? Is there
So, okay, yep. So if you look at this term here, right? And this constraint here. If those are allocated, so I just these things, if these are really large, these are good candidates to pick. And then I have to pick another alpha situation where the alphas are, where that constraint is really. Because I need to make sure that sum over yi alpha I remains 0. So therefore, I need to move into opposite directions. So I want to go a little bit through regularization before ending this class today, because it's actually quite useful and might give us a bit more of an understanding why on earth kernels do something useful. So let me move on. And so initially when SVMs were introduced, people started talking about, they don't suffer from the curse of dimensionality, and SVMs are somehow magic, and mind you, some of the authors of SVMs were also guilty of that crime, so it's not just the ignorant. But people were just really excited about it, right? Because, we have a large margin separator, we solve in this high-dimensional space, and in some cases you can actually prove that this thing lives in an infinite dimensional space. And the way to prove this, for instance, is you take kernel matrices with points in general position, and you show that these matrices always have full rank. And if I prove that for, regardless of how many dimensions, well, I know that I have an infinite dimensional space. But this is actually kind of scary because, we all know that the curse of dimensionality means, if I have a very high dimensional problem, it shouldn't work very well. And here exactly I have the situation where I have a very high dimensional problem and it works very well. So something else must be going on. So then started, or basically in the late 90s, the quest for let's figure out why those things work. So let's look at the loss. Well, these are some of the loss functions. So remember, we already had looked at the regularized risk functional. So we have basically an empirical error. So there's a soft margin error. And we have a penalty. So more generally, we have something of the form sum over I L, which depends maybe on xi, yi, and f of xi. And then I have a penalty and maybe I normalize that by the sample size. So this is the empirical error. This is like a so this is what you can look at when you get your programming assignment and you look at how well your algorithm performs on the data set that you're given. What you care about, however, for getting on the leaderboard is this. So basically what you care about is where the x's and y's are drawn from the Carlton distribution of x and y. So, in other words, if you could hack Carlton's computer and figure out what he has in here, you could, win everything, right? But you need to do that. So then the only thing that you can really hope for is to say, well, I'm assuming that, maybe simple is better. So smoother functions are better than very wiggly functions. Basically need to have some way of ordering what I consider a complicated function and what I consider a simple one. So my guess is we all agree that this is a really complicated function and this maybe is a much simpler one, right? So we want to have a device where I can insert this function and it gives me a number back. And I want this number to be large if the function is complicated. And I want it to be small if this function is simple. So maybe, here I get 100, and maybe here I get 3.2. And preferably I want that a function like this has a very small value, maybe 0.1. So this is what that regularizer up here is supposed to do. Okay. So this is exactly formalizing things. So let's see how we could actually get that, right? So here's a couple of candidates of what I can do. And by the way, so omega of f, if I have, my functions in feature space, so f of x, remember, is, for instance, w dot x or w dot phi of x. And then omega of f would be effectively some omega tilde of w. And it's, of course, parameterized by phi. So here are a couple of things that you could do. Who's worked with splines before? Nice. Okay. So basically, splines are ways of saying, well, I have some data points I might want to interpolate or maybe approximate what I see there. And I want to have a function that doesn't wiggle too much. For instance, I might want to find the minimum variation function that actually approximates the data perfectly. I'm actually sure all of you have worked with splines at some point. Who's ever used a drawing program where you draw curves and you have those Bezier curves? Okay, if you haven't, install GIMP or Photoshop or something like that. I mean, MS Paint isn't going to cut it, but yeah, GIMP would be quite wonderful. And you can basically draw curves. You can draw them really smoothly such that people like me can even draw things, right? So here's what they do. One way of measuring smoothness is I just of the first derivative, I square it and integrate it. And this will probably do something good here, right? Because, well, if it's really wiggly, then, you know, this is bad. If it's very smooth, it's good. I might also care about, well, hey, maybe my function value shouldn't be too large on average. So I just take the 2 norm of that. Okay, both things are good. Combining them makes it even better. So I just, you know, these 2 things to it. And so this is now an inner product in some weird space. And I'm now going to work out what happens. So the first thing that people did, and it's called regularization networks, is they said, well, you know, we don't quite know what the optimal solution of that problem is, but let's just plug in some functions, right? I can take sine and cosine, and I can work out, you know, its norm. I can work out, you know, its derivative, and just, you know, happily optimize away at it. So I'm just picking some expansion. F of x is sum over alpha I fi of x. This looks and feels very much like the representative theorem expansion, and as a matter of fact, later on we'll get that coming right out of it. But for the moment, let's assume these are some functions. Okay, so I can go and measure this. And remember what we had before is we basically had an operator p which mapped f into something a little bit more complex. And actually, this is a typo. This should be just dx of f, right? Okay, so it maps f into f and its first derivative. This is a linear operator. So matrix in function space. Okay. And then I can go and work out what the values are. And by linearity of this, I can pull the alphas out. Wow. And, well, I get this nice inner. So this looks very much like, you know, the standard inner product you would have. Remember what we had for SVMs. We had, you know, norm of w squared is sum over alpha I. If I could actually find some functions fi such that this condition here holds, right? Because if I had this, then I could just really equate what I have up here with the approach there. Okay. Now it turns out this is something that is very well studied in function analysis for people who solve differential equations. It's called a Green's function. And without going into a lot of detail, there is a very well-established machinery which lets you go from operators to things that solve exactly this condition. In which case, okay, so this is how it works. I basically take the Green's function for p transpose p, so it's the adjoint, and it basically, I pick a function k such that this condition holds, namely p transpose p k of x and dot applied to f is f of x. Okay, so this looks kind of familiar, right? Here we have something x a file. So I'm going through a lot of non-trivial math by essentially hand-waving and reasoning in terms of analogy. And that's simply because Otherwise, it would take a lot longer to go through it in detail, and I want you to get the intuition. There's a question.
So what is the dot you have in
The
here?
dot is because I have a function, so f, I mean basically the function is plugged in. So I could actually leave the dot out. But here, if I have a function of 2 arguments, and I specify 1, it's still a function of the other argument, and I want to say, well, hey, I want this to be treated as a function of, 1 argument still left. So that's a little bit like, let's say you have a matrix, and you multiply that matrix by a vector, you get a vector out of it, right? Or, you pull a column out of it. So I'm basically, this is like saying if I have a matrix M, which is, some object here, I could write M of I and dot. Or I could write, M of dot and J. And this would, pull out corresponding row or the corresponding column respectively. And for functions of 2 arguments, plugging it 1 turns it into a function of 1 argument. It does exactly the same as this here. So I'm not expecting you to, fully parse all the reasoning in the full mathematical detail, unless you've done physics before or done a lot of function analysis.
Could you clarify what is P star P there?
So P star is, P is this operator that mapped in our case f into f and dx of f. So Pf is f and dx of f. I could have another Pf, maybe some P tilde f, which maps it into maybe 3 times f, d squared x f, and maybe d42 x f. I could do that. And maybe, 0.9 times this. So these are all, reasonable ways of measuring smoothness, and they correspond to what I think about as smooth. Now, P star is the adjoint, so this is the operator equivalent of a matrix transpose. And you have to worry about complex numbers and so on, but it's basically a transpose. Now, what turns out to be the case, and I'm going to skip over spectrum and all that, is that I can actually rewrite this entire thing in Fourier space, at least for derivatives. So by Fourier Plancherel, basically energy in time and frequency domain. So that's what I'm exploiting here. So I'm writing this all in Fourier domain. And so I basically have the integral over the Fourier transform of f divided by 1 over 1 plus omega squared. So think of this P of omega as a penalty, which tells me where I would have to pay a lot if I had a lot of high frequency terms, or maybe where I have to pay a lot less if I have low frequency terms. So in this case, of course, P of omega looks like so. This is 1 over 1 plus omega squared. You might know this as the damped harmonic oscillator, if you've done physics. And so this is like a frequency filter. So it basically looks at the functions I want to use. And if I have very high frequency components, then dividing by something that's very small makes sense. And so this is why I basically then end up with a solution that's very well behaved. So think of this as, let's say I will have a regression or classification problem, and I know that my solution only has certain frequency components, then I can just engineer the solution accordingly. So to conclude with this, there's a nice theorem which basically says, if you have a kernel k of x and x prime that only depends on the difference between its arguments, then you can take the Fourier transform and you can immediately read off how it penalizes frequencies. Likewise, if I have an idea of how I want things to be smooth, I just Fourier transform that, and I get a kernel. It's this one-to-one correspondence. So let me give you a few examples, because that's probably a little bit more intuitive. If I have a Laplacian kernel which goes like e to the minus x prime, then the Fourier transform is 1 over omega squared inverse. So you get exactly this. If I have a Gaussian kernel, right, e to the minus 1 over x minus x prime divided by sigma squared, we know that, if I have a Gaussian and Fourier transform it, I get the inverse Gaussian again with the inverse variance. This is exactly what happens here. So you can see that by making the kernel narrower, my frequency range gets wider, that has more high frequency components. Whereas if I pick a really wide kernel, which means I have something that has only low frequency components. So that's exactly what's happening here. And on top of that, it also gives you a really easy condition to check whether something is a proper kernel or not. At least for translation invariant kernels, you just take the object, you Fourier transform, any zeros, well, you know that you don't have to worry about it. Any negative parts, you can just right away throw it out. So for instance, if I take something like the sinc function, this is sine x over x, and I Fourier transform it, you've probably done this at some point in electrical engineering, or maybe if you did physics, when you have basically a diffraction pattern, right? Then this corresponds to the Fourier transform of the unit interval. And we know that the unit interval, that the indicator function there is non-negative, so this basically means I don't know which frequency I pick, as long as it's bounded within some range. And this gives me the corresponding kernel. Okay. I'm not going to go into polynomial kernels because that would be just really complicated. And maybe we'll do some of the string kernels as some of the programming assignments. So basically these are really cool ways of computing attributes. And I think I'm just over time by a minute right now. Okay. So thank you very much.